Hey everybody, how's it going? Hope you are all having a great Global Hack Week, and I'm so glad that you decided to join for today's workshop on random forest classification algorithm. I think it's going to be a really fun time, and it's great to see you all here. If you want, go ahead and give us a comment and let us know where you're logging in from. I'll post one for myself. I'm logging in from California, USA. And yeah, if you want to let us know, is it morning time where you are? Is it nighttime where you are? Of course, don't get too specific, but it's great to see that we have such a global community of hackers. And yeah, maybe you can share a fact about yourself. Like, for example, do you like to the topic is random forest. Do you like to go in the forest, go for a hike, or do you like trees? Random forest actually doesn't have anything to do with those things, but it's kind of an interesting thing to know about all of you, what you like to do with your fun time, your free time. But yeah, so it's really great to see you all here. And this is the second section of a series of workshops on classification algorithms. And actually, before we get started with random forest today, I'm going to bring up a question that I asked all of you to consider in the last part, which was about our k-means clustering algorithm. And we were trying to figure out what the total score of our archery team was. Yeah, so let me pull that up, and we can check that out. Okay, so here's my screen, and you can see that these are all of the results that we had last time, where we were actually able to classify our data. We first classified it by rectangular coordinates, but then if we were to, I think this one was y over r. I forget what the polar coordinate transfer between this and theta was. Yeah, I think it's the arcsine of y over r. Yep, that sounds right. And so if we do that, we get a polar coordinate. Oh, it's right down here. That's great. So now if we copy our code from the rectangular coordinate system and we paste it into here, we should get 3 categories that are actually different than the last ones. We have to fit to df r and theta, which would be our polar coordinates system, yet the categories looking right. So before they didn't look right, but now they do. So, all right, now let's answer that question that I asked at the end of last session, which was, what is the total points of the archery team? Well, let's see how many hits that they made. So if we were to do length of df, we actually see that they made 3,000 marks. And we said that orange would be 15 points. This is category 1. We said that blue would be 5 points. So that's category 0. And green was 10 points. And so that's category 2. So does anybody remember from last time how to get the labels for our data frame? Any ideas? Well, we can actually use the df labels command. And, actually, I think maybe it's slightly different than that. Yeah, we have to use the k-means labels. And you can see that if we were to plot these in a histogram, we have three distinct categories, 0, 1, and 2. So let's loop through these labels. We can say for label in k-means labels, and we can have three conditions. If label equals 0, so this is category 0, we have if label equals 1, this is category 1, and we can have if label 2. So category 2. And to keep score, we'll create this score variable that will, our score will start at 0 and increment as we accumulate hits. So for a category 0 event, you might remember that the points we assign is 5 points. So we will increase score by 5. For category 1, we will increase our score by 15 because that would be orange. And for category 2, we will increment our score by 10 because that would be green. Now, if we print out the score, we see that our archery team scored 30,000 points when they went out to practice last time. And that's pretty impressive, but it would be hard for us to do that calculation and to know which targets they hit if it wasn't for our k-means clustering algorithm. So give yourselves a round of applause for figuring out this tricky problem. All right, everyone. So now let me outline the rest of the workshop and what we're going to be doing for today. So we are going to first learn a little bit about what is a decision tree and what is the random forest algorithm. Then after that, we're going to do a workshop together. And that will include a real example of a random forest classification algorithm. And once we're done with that, we'll finish up with a little bit of discussion of hyperparameter tuning, which is a process by which we can alter the parameters of our model to improve the fit. And you'll see that we actually are able to learn a little bit about that in our example. But before we do that, I want to quickly plug our check-in link and make sure that all of you are checked in for today. I see that there are 7 of you watching. And so if all 7 of you could click on this link and let us know that you are here, you'll get some valuable points for your guild. And it'll help us know what kind of content folks are interested in seeing at Global Hack Week. We definitely look at the check-ins to see what the interest level is in various things. And it really helps us track for our purposes as well. So thank you so much for checking in for this session. Okay, so with all that said, I'm going to go back to our session here, and we're going to share screen and show a slideshow. So here's the slideshow. There you go. So this lecture portion is on decision trees and random forest algorithms. So you might be wondering, what is a decision tree? So a decision tree is a supervised learning algorithm based on a tree model. And so we are going to be giving a tree diagram to the computer. And actually, the computer could determine an optimal tree diagram itself, and that's where the learning comes in. Um, Actually, I think this should say unsupervised because it's possible to also give a tree model without having the computer learn from examples. So actually, let's scratch that portion out. 1 second. Okay, let me reshare my screen. So we could use a supervised learning approach, or we could give a predefined decision scheme. And that would also be considered a uh, algorithm here. Oh my goodness! Now it's covering the. There's always a technical error. Everybody knows that, but there's always something that goes wrong, right? Let me quickly fix that so that everyone can read the slide. Sorry, everyone. Thank you for bearing with us in that. And yes, so if you can see now, this is an example of a decision tree taken from Wikipedia. And a lot of people think Wikipedia is not a very reliable source, but I think it's just fine. And so you can see that we are building a kyphosis model. And kyphosis is a complication of spinal surgery, a possible complication. It doesn't happen every time there's spinal surgery, but it does happen some of the time. And this decision tree model is designed to predict whether kyphosis was present in a patient that underwent spinal surgery. And the predictor variables that are given are start, and the variable start is the vertebra where the surgery took place. So that could be on your fifth vertebra, for example, or your 10th vertebra. I forget how many you have, but you have a lot of vertebra. It seems like you have at least 15 based on this plot here, more than 15 actually. But the age variable indicates the age of the patient when they underwent surgery. So you could imagine that these variables would be important because it's said that the higher up your fracture is in your spine, the more dangerous that is. It could paralyze you or create some other bad complication. So it makes sense that the starting vertebra would be important. And age also makes important sense as a predictor variable for this disease because we all know that younger people, generally speaking, have less of a tendency towards disease or complications from surgery. So these two variables are really, makes sense that they would predict kyphosis. And you really want to make sure that your variables make sense because when we do just machine learning on variables, there's always a tendency for the machine to find a pattern where one does not actually exist. And if we were analyzing variables that seemed to be totally unrelated to kyphosis, and we got a great model out of it, we'd really need to question why these variables were able to predict kyphosis so well. It could just be a statistical anomaly. So we want to think through why our variables would be good predictors. Okay, so now let's look at our decision tree. And the decision tree is made up of these nodes. And then these are the leaves over here. So you have these branches and these different possibilities. And so let's start at this decision over here. Is the start vertebra larger than 8.5? So did the surgery take place on the ninth vertebra or larger? Yes or no? And in order for that to, the model to make that decision, it needs to have the start variable. And then once it has that for a particular case, if that answer is no, then it will follow this branch here and to the second level here, and just basically say that there's a 58% chance that the patient had that outcome, this kyphosis outcome. On the other hand, if the start vertebra was 10, for example, you would follow this line, the left line, the yes decision, and go to that node. And if the start vertebra is 10, as we were saying, you would then go this way and so on. So yeah, that's kind of how this would go. So like, let's, for example, think about what would happen if we were on the 10th vertebra and we had a patient who was 8. And so if we looked at that, we would see, oh, we go through to the left side on the first node. The second decision, we go to the right side. The third, we go to the right side. And the fourth, we would go to the right side. And we'd find that we have a probability of 0.57 that the patient had kyphosis. Okay, so this map over here indicates the probability distribution of kyphosis, and you can see that this decision tree has a probability distribution where the lower the variable of start and the lower the variable of age, and the higher the variable of age, generally speaking, the more likely there is to be some probability of kyphosis. So that's something to think about, certainly. Okay. Now, what is a random forest? Well, a random forest is a random distribution of trees. And you don't want to get caught in a random forest because you'll never find your way out. No, I'm just kidding. That's not what a random forest is. A random forest is not a forest of randomly placed trees. It is, at least not in computer science. In computer science, a random forest is an ensemble of decision trees. So you could have many different kinds of decision trees, and they all have slightly different threshold values, slightly different structures, and there's a procedure by which these trees will vote on the outcome. So if trees 1 and 2 think that kyphosis is present, and tree 1 thinks that kyphosis is not present, then majority rules and kyphosis present will be the prediction of the random forest. So the idea is that you would have so many more opportunities to make the right call, and it's going to lead to a less biased result, a more accurate result when you do that. And so, yeah, that's basically what a random forest is. And we're going to explore a real example of a random forest very soon using the kyphosis data set. And if you'd like to get a head start looking at that, I'm going to post a link that you can check out. It's a link to today's lesson, which is on random forest. And have some folks in the chat. Hello, Alvin. Good to see you. Hi there. And I saw someone else send a very cute emoji in the chat. So thank you for sending that. And I love to see it when the chat is, active and folks are talking. So maybe over the break, if anyone would like to make a chat, please feel free to do so. Just we ask to keep it respectful and kind as our community always does. So I'm going to post the link to that workshop. Actually, probably over the break, I will probably clean up this a little bit and make a blank one, so that we can actually use a blank template for today. Just so that you can follow along without necessarily having the answer right in front of you. Although if you'd like to have the answer, I've had that posted too. So it's totally okay to do that as well. All right. So let me go ahead and start with our break, and we will come back in 15 minutes after the break is over. Hi there, everyone, and welcome back to the stream. I hope you had a great break while we were away, and wanted to reopen the stream with a quick ask for a comment. And the comment is, what is your favorite color? And I'm going to put my favorite color in the chat. And yeah, feel free to share your favorite color in the chat. And that's just a way we can get to know each other better in the chat. So, all right. Now let's move on to the second part of our workshop for today, which is about random forest and decision trees. And true to my word, I was able to create a new blank document that contains none of the code from last time. The only difference would be that we are going to put the libraries in, because I don't want to spend time showing you how to import Python libraries. If you want a tutorial on that, I created a series on data science in the last month's Global Hack Week, and there is some great information there if you're getting beginner there. But just want to highlight some answers in the chat. So Tark says dark blue, and CDUY says black. So we have a lot of dark colors, including my answer actually, in the chat. If anyone likes a light color like orange or yellow or white, please respond. We'd love to hear from you and see if you're out there. All right, everybody. Well, let's go ahead and continue along. So if you have the repository for our lesson today, let me just I forgot to push this blank template to the GitHub repository, but it's now pushed so you can see it up there. What we're going to do first is we're going to read in the data, and you can see in the left margin here that I've placed kyphosis.csv in your repository so that you have access to this data. And the data is delimited with commas, and the first column being kyphosis. So if kyphosis is absent, the string absent will be there. If it is present, the string present. Those are the only two options for the data. The age is placed in column number 2. And then number, we actually won't be using number for this one, but we will be using the start. And the reason for that is just to keep things simple and also keep them comparable to our Wikipedia example. So we're going to use pandas now to read in the kyphosis data set. So there you go. And if you don't have a interpreter for your Python, for your Jupyter notebooks, I highly recommend VS Code, which is what I'm using right now. And I also highly recommend Anaconda. I just placed a link in the chat to anaconda.org. These are both locally hosted interpreters for your Jupyter notebook or Python notebook. And that's a great way to read your code, save your code, and it's more customizable and faster than using a cloud-based product like Google Colab. But if you're more comfortable using a cloud-based product, I think that's totally okay. And if you'd like to get some help with that, please send a chat. I'm sure many folks here are working with all of these different technologies and would be happy to help you get started. But for now, let's go ahead and look at what this data shows when we load in this CSV. And you can see exactly what we saw in our CSV. Reader, we saw all these 4 columns, and the first column on the left is actually what we call the predictor column, and so the predictand, excuse me. And so that is what's being predicted. And the next columns on the right are the predictor columns. So we have age as a predictor of kyphosis, and start as a predictor of kyphosis, and number, we will actually eliminate that one by simply typing dot drop number axis equals 1. That will drop the number column from our data frame. And now we're just going to simply save this data frame into the df variable, so we can call it later. Okay, everyone. So if we scroll back up to the top, you see we have this diagram that we took from that previous example we saw in part 1 of today's lecture. And we're going to actually mimic this decision tree using simple Python code. So I'm going to create a function called simple tree, which is just this simple decision tree that's been already drawn for us. And simple tree is going to take the 2 variables which this tree has, which are age and start. Okay. And so first we're going to program the first node. And that first node is going to be whether start is greater than or equal to 8.5. So we're going to use a condition statement. We're going to say if start is greater than or equal to 8.5. And actually, let's start with the case of whether start is less than 8.5. So that would be the right-hand side. If start is less than 8.5, then we will have a 58% chance of seeing kyphosis in the patient. And to represent that, we're going to use a binomial PDF, probability distribution function, given to us by the NumPy library. So if you scroll up here to the top, you'll see that we've imported the NumPy library as NP. And that gives us access to the binomial distribution PDF. So we use np.random.binomial to get that. And we only want 1, and because we only are analyzing 1 case at a time. And the probability of a yes will be 0.58. Okay. So let's now program the second node. So this is what will happen if we don't go from the first node. We'll go to the second node. If start is greater than or equal to 8.5, this condition statement won't run. Actually, we want to write return here. But in the second node, if we have this one, we can see that start is greater than or equal to 14 results in a 0% chance of kyphosis. So let's cover that case. If start is greater than or equal to 14, we'll return 0. And if not, well, we're then on to the third node. So this is the third level of the tree. There are a total of 4 levels. And on the third level, if age is less than 4.6, that's pretty low age. There's also a 0% chance of kyphosis. So we can say that if age is less than 4.6, return 0. But if not, we'll go to the fourth node, our fourth and final node. And if age is greater than or equal to 9.2, then we will return our random binomial distribution with a 1, a probability of 0.14. But otherwise, if we go to the right-hand side, we'll get 0.57. So we can just return 0.57 as our probability if not. So this is our simple tree. And let's give it an example just to test our simple tree and see if it works. So let's say we have age of 5 and start of 10. So we expect this model to go through the first case, start 10, so yes. Start greater than or equal to 14, no. Is age less than 4.6? No. Is age greater than 9.2? No. So we should get a 57% chance. So we should pretty much see sometimes 0, sometimes 1. And that's exactly what we see when we run this. I'm really lucky that it showed up exactly like that, sometimes 0, sometimes 1. But that's exactly what we expect to see with our simple tree decision algorithm. And so this is a form of artificial intelligence because we are asking the computer to make a prediction based on some knowledge. But how can we evaluate the accuracy of our decision tree and see if it's really all that good? So first, we're going to need to generate some predictions. So let's type kyphosis prediction, which is kyphosis pred. Pred is often the abbreviation of prediction for machine learning. And we're going to loop through every data point in our data frame of values. So let's first print these and see what they look like. So each time we have a new data object, it is actually a list object, and it has 3 elements. It has the kyphosis real, so not the predicted kyphosis, but the actual kyphosis, whether it's absent or present. And then we have the age, which is listed in the second column, and the start, which is the start vertebra of the surgery. And you can see that when we produce simple tree, let's print simple tree instead. We can use data columns 1 and data column 2 because the first column is data 0. We can produce a series of 0s and 1s, and these can be compared to kyphosis. So these are our prediction, and we will say actual is whether or not the data 0 column is equal to present. That will tell us whether 0 if there is none, if it's absent, and 1 if it is present. And we can just see that here in column 0. So if prediction is equal to actual, meaning that our decision tree model made the right call, the right choice, another phrasing, we can say kyphosis prediction, we can append a 1 here. And if, on the other hand, our prediction is not equal to the actual, so this would mean that our decision tree model missed the mark, or in other words, it wasn't correct, we could append a 0 here. And the answer key, I think, does a very similar thing to what we're doing here. But then if we were to sum our kyphosis predictions and divide by the length of our kyphosis predictions, we should get, in fact, we do get a accuracy score. So we see that our accuracy score is 0.76. And so if we were to multiply by 100, that would say 76% chance of getting that right. But let's actually repeat this process, because if you see, if we run it again, we get a slightly different answer, 79%. And in fact, if this model is partly stochastic, which means that it's partly random. And so it's possible that we could get a different result every time we run this model. So let's create a function called getAccuracy. And this will simply run our code, but do so repeatedly. So now we can return the accuracy score. And when we make a loop, let's say we want to do this about, well, let's do it 100 times, because I think 1,000 might be a little overkill. These are our accuracy scores. We can append all of the results of our getAccuracy function to this accuracy scores, and then we can see what the results are. and really print out some statistics about our accuracy score, such as the mean and the standard deviation. In fact, when we do that, we get a distribution that, given enough time, we would expect it to be fairly normally distributed, because we are, after all, taking a statistic from a sample, a random sample. And so, yeah, we get something that looks kind of normal, is centered around 78% accuracy, and 95% of the values lie between like 72 and 84% accuracy. So our model is about 78% accurate. And that's pretty good. But we're going to see if random forest can do any better. So let's actually test that in this next stage. So the next stage is for us to actually create a random forest algorithm. And first, we're going to have to split our data, because random forest is a supervised algorithm, supervised learning, machine learning algorithm. And so let's create X, which is going to be our features, or in other words, the variables we will use as predictors. And that will be all of the things in our data frame except for kyphosis, which is a predict band. And we want to also have Y, which will be our predict band, which is kyphosis, and whether or not it is present or absent. And so let's go ahead and split this data. And we're going to use the train test split function. What's that, you might ask? Well, we imported that in the very first cell over here, this random forest classifier. So we used the sklearn Python module to import that. We did sklearn.model selection, import train test split. And this is going to randomly divide our data into several categories, which will be listed. So let me list those for you now. So we have our X test, X train, Y test, and Y train. And so our X test is going to be the features that we will use to test. Oh, actually, I think I have this backwards. We should start with train. So that's going to be the features we use to train the model and calibrate it. In other words, those are the examples that the model will learn from. And X test will be the features that we test the model out on to see if it holds up to snuff. And Y train will be the kyphosis predictions that we train on, those examples, successful examples. And then Y test will give us a new sample that will be tested and evaluate the accuracy. So in train test split, we put X and Y. And we also need to put test size, which will tell us the size of test relative to the whole data set. And it's very common to use 0.2 for test size. So we're going to use that today. Actually, we don't need to write this in because that's what the default value is, but I just wanted to show that to you in case you wanted to play with that later and see how it impacts the results. But let's go ahead and run this code. And now our data is successfully split. So we can move on to training our random forest algorithm. And if we go ahead and start with that, we can use the random forest classifier model, which is imported from sklearn at the top. You can see in the slide here. And so then after importing that classifier model, the next step is to fit the model to the training data. So this is creating a new random forest model. And then we will train the model on the training data set. And finally, give an accuracy score similar to what we made the decision tree. So this is exactly the same type of thing, but it's going to be done for us by the random forest classifier. So when we run this data, we get a score of 0.9. So you can see that a random forest of trees is much better than a single decision tree, even one that has been carefully, thoughtfully optimized, like the decision tree that we looked at earlier. Even compared to this tree, a random forest will outperform that tree. And so that's all we have for today. Those are basically the meat and potatoes of decision trees and random forests. But I'm actually going to cover one last topic, which is called hyperparameter tuning. And we don't actually have enough data to do robust hyperparameter tuning in this example, but I wanted to give you a little bit of a taste of what it's like to do that and go through that process. So let me stop sharing, and I'm going to show you a Wikipedia page on the random forest classifier. Okay, everyone. So the random forest classifier is defined in the sklearn documentation, and let me pull that up for you. And there are many, many features that you can edit and that are by default set that can be messed with and changed around. So for example, this parameter n estimators is the number of trees in your forest. So by default, and in our example, there are 100 decision trees, but we could create an arbitrarily large number of trees in our forest by adjusting the value of this parameter. The criterion by which they are split is an option to change. And there's also max depth, which is the maximum depth of, or in other words, like the number of nodes, the layers of nodes you can have in your trees. There would be a minimum samples, how many you must have in order to actually create a split in the tree. And so, I'm not going to go through all of these because there's a lot of them, but these are all slightly different things you could tweak in the model to try and get a better fit. And so we're going to be exploring one of these parameters today, which is called n estimators, and we're going to see if we can get a better fit. So let me go ahead and share screen and show you how to do that. Okay, everybody. So we're going to check the ideal number of estimators, and it could be 100, but it might not be 100. And so we're going to take a look at that. So there's an example of how to do this in the notebook. But yeah, I just want to maybe go through this with you together. So I want to first define a place to stop because we can't sample the entire space of estimators because theoretically we could have infinite trees in our forest, and that's not possible it's not a case that the computer can actually check. So let's just stop at 500 because we've already tried 100 and maybe some larger number might be better. Let's see. So now I'm going to store scores, which will keep track of all of the estimators that we try. So I'm going to use max estimators divided by 10 to create a new scored matrix. And we're going to store all of the scores from our hyperparameter tuning in that array. And the next thing we'll do is create a loop that is going to go through and say that for every I between 0 and the max estimator, skipping every 10, we're going to basically do the whole entire fitting process over again. So we create our train test split. We generate a random forest model. a new one, we generate a new fit for the model, we generate a new score for the model, and sorry about this, everybody. Just need to fit a little bit. And then we're only going to vary the number of estimators that we use. And we're going to use I for the number of estimators. So we might start off with 10 estimators. Let's add one to this just so that we're not starting with 0 estimators, because obviously 0 estimators is not going to work. It's not going to give us a good model. So yeah, let's store the accuracies in some kind of list. So actually, I think last time I wanted to do this, I actually used a second loop to just give 100 samples. And that way we could really sample this each estimator level very well. So now we can just add this score to the sample scores array. I'll score J, why not? And then when we exit out of this 100 samples of that estimator level, we can just take the mean of those sample scores. So this will give us kind of a robust estimate of what that will be. So let's print these out for every single level. Like maybe I should have used an integer here. And it's going. So remember that the model is actually testing 1, 11, 21, 31, 41, and so on. So we're going to get a different score for each of these. But generally speaking, as the number of estimators goes up, we would expect to see a larger score. Okay, and so these numbers are going to look different than the example we gave up here, because what we did up here was just a single train test split. Now we're doing hundreds of them. So you can see at 100, when we reach 100, we get a uniquely good fit compared to all the previous ones. And that's consistent with what we found in our original example, where a number of estimators being 100 was a pretty good fit. You can see even 120 is better than 100. So we haven't quite found the maximum at 100, but it's pretty good compared to the other results. And the more estimators we include, the longer it will take for the algorithm to run. So there's always a competition between the simplest model, which will always be the fastest model, and then on the other hand, the most accurate model, which is usually taking more training. And we spoke about that in the last part of this series, but generally speaking, more training time, more complexity will lead to a more accurate, more powerful model, although that's not always the case. So this is just one example of how you can use hyperparameter tuning to really figure out what is the best variables to put into your random forest. And if you want, you can continue to tweak this model, maybe see if there's a better, for example, a better max depth parameter. Is there a particular max depth parameter that will both save a lot of time in the algorithm and also be pretty accurate compared to our best results? So I encourage you all to take a look at that as well. All right. So does anybody have any questions about this before we finish for today? right. Well, in case you have a question, please feel free to send a message in Discord, or you can even send me a message in our next workshop, which will be part 3 tomorrow. So let me go ahead and share with you the registration link for tomorrow's workshop. And after doing that, we're going to log off for the day. But thank you all so much for coming today and for chatting and learning. And here's the link for tomorrow's workshop. And goodbye. Thank you very much. Have a great rest of your hack week.